Hello and welcome to Math Zone African Motives. I'm your tutor, and today we're tackling some mixed differentiation examples. Our goal is to solidify your understanding of various differentiation techniques by working through a few challenging problems. By the end of this tutorial, you will be able to apply the product rule, chain rule, implicit differentiation, and logarithmic differentiation to solve complex problems. Let's dive into our first example. We're going to start with example 2.25. The question asks, if y equals a squared over 2b times sine inverse of bx over a plus x over 2 times the square root of a squared minus b squared x squared, prove that di dx equals the square root of a squared minus b squared x squared. This problem requires us to use the chain rule and the product rule. Let's list the formulas we'll be using. First, the derivative of the inverse sine function. The derivative of arcs in u is 1 over the square root of 1 minus u squared times du dx, which is the chain rule part. Second, the product rule. The derivative of a product of two functions, u times v, is u times the derivative of v plus v times the derivative of u. Let's apply these to find the derivative, di/a. We'll differentiate each term in the original expression. Let's start with the first term. In the first term, a squared over 2b is a constant. The derivative of arcs in bxa is 1 over the square root of 1 minus bx over a squared times the derivative of bxa, which is ba. So the derivative of the first term is a squared over 2b times our inverse sine derivative. Now for the second term, we'll use the product rule. Let u be x over 2 and v be the square root of a squared minus b squared x squared. The derivative will be u times the derivative of v plus v times the derivative of u. Using the chain rule for v, we get 1 over 2 times the term in the parenthesis to the negative 1/2 power, times the derivative of the inside, which is negative 2b squared x. Putting it together with the product rule, we have u times div dx plus v times du ds. Now let's assemble the full derivative by adding the result from the first term to the result from the second term. It looks messy, but now we'll simplify. Let's start with the first term. In the numerator, a squared times b over 2b times a simplifies to a over 2. The denominator becomes the square root of a squared minus b squared x squared, all over a, which is just the square root over a. This gives us a squared over 2 times the square root of a squared minus b squared x squared. Now our full expression for di dx is much cleaner. It's the simplified first term minus the simplified product rule terms. Since all three terms have a common denominator of 2 times the square root of a squared minus b squared x squared, we can combine their numerators. The numerator becomes a squared minus b squared x squared, plus the quantity a squared minus b squared x squared. Adding these gives 2 times the quantity a squared minus b squared x squared. The 2 in the numerator and denominator cancel out. We are left with a squared minus b squared x squared over its own square root. Remember that a number over its own square root is simply the square root of that number. So, our final answer is the square root of a squared minus b squared x squared. This matches the expression we were asked to prove. We have successfully verified our answer using the memo. In this problem, we practiced using both the chain rule for inverse sine and the product rule. Now let's move on to example 2.26. This problem introduces a new technique. The question is, if x to the power of a times y to the power of b equals x plus y to the power of a plus b, prove that di x equals y over x using logarithmic and implicit differentiation. We have variables raised to constant powers on both sides. When we see this structure, especially with a product on one side and a sum in the base on the other, it's a strong hint to use logarithmic differentiation. This allows us to bring down exponents and simplify products. The first step is to take the natural logarithm of both sides. Now we can use the properties of logarithms. The logarithm of a product is the sum of the logarithms, and the exponent inside a logarithm can be moved to the front as a multiplier. Applying these rules, we get a times ln x plus b times ln y on the left and a plus b times ln x plus y on the right. This equation is much easier to differentiate. Next, we will differentiate both sides of this equation with respect to x. Remember that we must use the chain rule for any term containing y. The derivative of a times ln x is a over x. The derivative of b times ln y is b over y times di is dx. On the right, we use the chain rule again, which gives us a plus b over x plus y times the derivative of the inside, which is 1 plus di. Now, our goal is to solve this equation for di/dx. First, let's distribute the term on the right side. This gives us a over x plus b over y times di/dx equals a plus b over cos y plus a plus b over xy times di by x. Now gather all the terms containing di/dx on one side and all the other terms on the other side. Let's move the di/dx terms to the left. Subtracting a plus b cos y times di over x from both sides, we get this equation. Factor out di dx from the left side. Then find a common denominator for the fractions inside the parentheses. On the left, the common denominator is y times sx plus y. This gives us bx plus by minus ai minus by all over y times sata x plus y. On the right, the common denominator is x times x plus y, giving x plus bx minus a. Notice that some terms in the numerators cancel out. The by terms cancel on the left, and the x terms cancel on the right. This simplifies to di/dx times bx minus ai over y times x plus y equals bx minus ai over x times x plus y. To isolate di/dx, we multiply both sides by the reciprocal of the fraction on the left. Multiplying by y times sxy and dividing by bx minus ai, we can see that a large number of terms cancel out. The term bx minus ai cancels, and the term x plus y cancels, leaving us with our final result. Dx equals y over x. And this proves the statement. We've verified our answer. This example beautifully demonstrates how combining logarithmic differentiation and implicit differentiation can solve problems that would be nearly impossible with just the product and chain rules. Our third example is example 2.27. We will explore 3 different methods to solve this one. The problem is, given y equals 5 to the power of 5 to the x, determine diag. This is a tower of exponents, and it's a perfect candidate for differentiation. Let's start with the method described in the memo, which is using logarithmic differentiation once. Method 1 involves taking the logarithm of both sides. This brings the top exponent, 5 to the x, down. So we have ln y equals 5 to the x times ln 5. Now we differentiate with respect to x. The derivative of ln y is 1 over y times di dt by s. On the right, ln 5 is a constant, and the derivative of 5 to the x is 5 to the x times ln 5. Now we just need to solve for d dx. Multiply both sides by y. Remember that y was 5 to the power of 5 to the x. Substituting that back in, we get our final answer. 5 to the power of 5 to the x times 5 to the x times ln 5 squared. This is a very common pattern for this type of problem. Now let's explore method 2, which involves taking logarithms twice. This is an alternative approach. Again, we start with our equation y equals 5 to the power of 5 to the x. We take the first natural log, which simplifies to ln y equals 5 to the x times ln 5. The right-hand side is still a product with a variable in the exponent. To simplify this further, we can take the natural logarithm of both sides again. The logarithm of ln y becomes ln of ln y. On the right, ln of a product is the sum of the logs. The exponent on 5 comes down, leaving us with x ln 5 plus ln of ln 5. This equation has no exponents with variables and no products or quotients of functions of x. It's much simpler to differentiate. Using the chain rule, the derivative of the left side is 1 over y ln y times di ya. The derivative of the right side is simply ln 5, since ln 5 is a constant. Now we solve for di's dx. Multiply both sides by y ln y. Then substitute back for y and for ln y. Since ln y is 5 to the x times ln 5, we make that substitution. The ln 5 terms multiply to ln 5 squared, giving us the exact same result as before. Both methods lead to the same correct answer. Finally, let's look at method 3, which uses the chain rule directly. This requires us to recognize the function as a composition. We can see the outer function is an exponential 5 to the power of u, and the inner function, u, is 5 to the power of x. The chain rule states that di dx is di du times du dx. The derivative of u with respect to x is 5 to the x ln 5. The derivative of y with respect to u is 5 to the u ln 5. Remember to substitute u back with 5 to the x. Now we multiply these two parts together. Di slash dx equals di du times du slash dx, which is 5 to the power of 5 to the x, times ln 5, times 5 to the x times ln 5. This simplifies to the same result once again. We've verified all three methods. This example shows that sometimes there are multiple valid paths to the solution. The key is to choose a method you are comfortable with. Let's conclude with example 2.28. This problem combines logarithms of different bases requiring an extra step. The question is, if y equals the natural logarithm of log base 2 of x plus log base 2 of the natural logarithm of x, determine d dt d dx. Before we differentiate, we need to handle the log base 2 terms. We do this using the change of base formula for logarithms. This formula states that the logarithm of x to a base a can be written as the natural logarithm of x divided by the natural logarithm of a. Let's apply this to the two terms in our expression for y. The first term becomes ln yc divided by ln 2. The second term becomes lev divided by ln 2. Notice that ln 2 is a constant. We can simplify the first term even further using the logarithm property that ln ab equals ln a minus ln b. So y becomes ln x minus ln 2 plus ln x over ln 2. Now this expression is in terms of only natural logarithms and constants, which we can easily differentiate. Let's find di dx. We differentiate each term. The derivative of ln x is 1 over ln x times the derivative of ln x, which is 1 over x. The derivative of ln 2 is 0 because it's a constant. For the third term, ln 2 is a constant multiplier, and we differentiate ln x again. The result is 1 over x ln x plus 1 over ln 2 times 1 over x ln. We can see that the term 1 over x ln x is common to both parts. We can factor it out. This gives us our final answer, 1 over x ln x times the quantity 1 plus 1 over ln 2. The answer is verified using the memo. This problem highlights the importance of simplifying a function first, using logarithm properties, before you even begin differentiating. This can make a complex problem much more manageable. Let's quickly recap what we've learned today. We started with a complex trigonometric and algebraic expression, showing how the product and chain rules work together. We then explored the power of logarithmic and implicit differentiation for equations with variables in the exponents. Finally, we saw how simplifying functions using change of base and logarithm properties can make seemingly daunting problems much easier. I hope this step-by-step tutorial was helpful. The key to mastering these techniques is practice. Thank you for watching this Math Zone African Motives tutorial. Subscribe for more videos to help you excel in your studies. See you next time.